Hi guys, so in this video we're going to take a look at derivatives of polynomial functions. And we'll jump straight in with a couple of examples. So let's consider the function f of x equals x squared. That gives us that the function at x plus h is equal to x plus h squared, which equals x squared plus 2xh plus h squared. When we plug that into our derivative formula, f prime x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h, we get the limit as h approaches 0 of x squared plus 2xh plus h squared minus, and in this case we only have the one term, x squared. It is a good habit to put your minus in brackets just because it reminds you that you have to apply the minus to every term. Okay, and then simplifying that one, we get the limit, those terms cancel, we've got 2xh divided by h, so 2x, plus h squared divided by h is h. Now since that h is going to disappear, that whole answer is 2x. Okay, we'll do that again, but this time for a cubic, basic cubic function, x cubed. That means our function at x plus h is x plus h cubed. And that's x cubed plus 3x squared h plus 3xh squared plus h cubed. And that means that our derivative is going to be the limit as h approaches 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed, all divided by h. And that's going to give us the limit as h approaches 0 of 3x squared plus 3xh plus h squared. Now in the limit that h approaches 0, each of those last two terms becomes 0, and that gives us 3x squared. If we do this enough, we find a pattern. So we already know that when our function is x squared, our derivative is 2x, and when our function is x cubed, our derivative comes out to be 3x squared. If we continue on, if we had as our function x to the power of 4, we would find that the derivative function is 4x to the power of 3. If our function was x to the power of 5, our derivative would be 5x to the power of 4. It's fairly simple to see that there is a pattern to these. If our function is x to the power of n, then our derivative is always going to be nx to the n minus 1. This is our first rule, which will allow us to avoid having to use the first principles method to find every derivative. We can simply use this rule and apply it to any polynomial power and jump straight to the answer. And there's a reason that this rule works. If we consider a square that is changing size, So its side length is changing, and we want to know how quickly the area is changing in response. Well, for a square to change size but still remain a square, you would have to add a little bit along two sides. And then if you did it again, you would get a slightly bigger square. But if you don't do it along two sides, it won't be a square anymore. And so the rate of change of the area with respect to the side length, if you ratio those two things, what you get is that at any point the square is getting bigger by 2s. This is when we consider the original formula for the area is always s squared. This second formula is our area, and this first one here is the rate of change, the instantaneous rate of change, the derivative of that function. So it makes sense that the derivative of s squared needs to be 2s. And if we expand that up to 3 dimensions, so we start with a cube of side length s, and we're imagining that cube gets bigger, okay, what we would need is for that cube to expand in each of the 3 dimensions. So we'd have to add an extra layer to each of 3 sides. So we start with volume equals s cubed, but if we look at the instantaneous rate of change of the volume with respect to the change in side length, we find that the volume that is being gained at that moment is equal to 3 times one of the sides, which is going to be s squared. And of course, although it's hard to imagine physically, you can expand this up to any dimension you like. If you had a 4 cube, a cube in 4 dimensions, each of the surfaces would be a normal 3-dimensional cube. And you would have to add one of those on to each of the sides in each of the 4 dimensions. So you would have 4 lots of s cubed being added on at any moment. So what we're going to do now is summarize a couple more rules that will help us to differentiate polynomial functions. So the one we've already worked out is that the derivative d dx of x to the power of n is equal to n times x to the power of n minus 1. We can expand this out. The derivative of k times x to the power of n is just k times n x to the power of n minus 1. So constants out the front of these terms don't affect the derivative at all, they just remain there multiplying out the front. We can also check, and you can do this yourself by trying it with first principles, that the derivative of 2 functions, f of x plus g of x, so this could be 2 terms in a polynomial, x cubed plus x squared, is equal to the individual derivatives of the 2 functions added together. We can also write this in a second way, and that's that if we have 2 functions where we're finding the difference between those functions, that the answer will just be the difference of the 2 derivatives, individual derivatives. Combining all of these together, what we actually get is one big formula that says that the derivative of a f of x plus b g of x is just going to be equal to a f dash x plus b g dash x. What this means for us in general is that if we have any polynomial function, for example 3x to the power of 4 minus 2x cubed plus 14x squared, that we can find its derivative function by considering each term separately. So 3x to the power of 4, we take the 4 and multiply it out the front and drop the power by 1. So that gives us 12x to the power of 3 minus 3 times 2 is 6x to the power of 2, because we drop that power by 1, plus 14 times 2 is 28 times x. And there's only one other rule that we haven't really mentioned, and that's a fairly trivial one, and that's that the derivative of a constant is always 0. All of those rules together allow you to find the derivative of any polynomial function without resorting to first principles. You can skip straight to the answer.